Hello everybody and welcome back to RSW Tutoring. Today we will be taking a look at the general term formulas for arithmetic and geometric sequences. So before we start, I'd like to establish the difference between a finite sequence and an infinite sequence. So these are some basic concepts. If you feel comfortable, please feel free to fast forward and get on to the more difficult concepts. So a finite sequence is when we have a fixed number of terms. For example, 5, 3, 1, -1. So a common difference of -2 each time. But we have four terms, so this is a finite sequence. The moment we add an ellipsis, which is these three dots right here, it means that the sequence continues on infinitely, and therefore it is an infinite sequence. I'd also like to clarify the concept of the general term and how we write it in mathematics, especially in this chapter. It's represented by un, and un essentially precedes the equal sign in the equation that we established for a particular sequence. So for example, if I had the sequence 2, 4, 6, 8, on and on, these are really basic examples, by the way, where we have a positive 2 difference, then our un would be 2n, or 2 times the term number being 1, 2, 3, 4, etc., etc. And if we wanted to find the fifth term, let's say all we have to do is say u5 equals 2 times 5, which equals 210. So I hope that clarifies the basic concepts, and we will get into more basic concepts, but for now, that is it. In terms of the actual material itself, so let's establish the difference between an arithmetic sequence and a geometric sequence. So let's take the following example: 100, 102, let's say 104, 106, etc., etc. So now, how would we establish the general term formula for this arithmetic sequence? Well, we see here that each time we're adding 2. So therefore, we can manipulate this repetitive addition that we have of plus 2 into an equation. So what you usually tend to do in arithmetic sequences is you tend to take this value, 2, and you tend to multiply it by the term number and add the difference. This is usually your most common and easiest type of question that you tend to get on tests. So in our case, it would be un equals 2 times n plus the remainder, which would be, in this case, 98 100 minus 2. Now, let's see if that really works. Let's just say, let's configure it to u4. So for example, 2 times 4 plus 98 equals, well, let's do the math here. That would be 8 plus 98, which would give us an answer of 106. Well, guess what? This answer corresponds to this, meaning that we have done a correct job of actually establishing the equation. So this is a very simple example. That was an arithmetic sequence. So an arithmetic sequence is when we continuously add the same value to get to the next term. Now, a sequence is geometric when each term is multiplied by the same value to get to the next term. For example, in this case, we have 5, we have 10, we have 20, we have 40, we have 80, etc., etc. Now, this is a geometric sequence because each time we're multiplying by 2, not adding, but multiplying by 2. And in order to establish a general term sequence for this, what we usually tend to do is take the first term and multiply it by the actual multiplier. So in this case, it would be 2. And this we tend to raise to the power of n minus 1 usually. This does not happen always, but usually the most common form of geometric sequence will take this shape. Why? Well, if we see here, we multiply 5 by 2 to the power of n minus 1, because the first term, when we substitute it into the actual n value, so the term number for this is 1, and when we substitute it, we get 5 times 2 to the power of 0, and 2 to the power of 0, according to the general power rules, gives us 1. So 5 times 1 gives us 5. What about for the second term? Let's see if it works for the second term. Let's try u2 equals 5 times 2 to the power of 2 minus 1. And this gives us, well, you see here 2 minus 1 is just simply 1, and that will give us 10, and so on and so forth. Now, I know it's kind of difficult to understand, but that's the general concept that you have to follow. Let's do some more examples to consolidate your knowledge. Let's start with this one. This one's pretty simple. Let's do 3, 6, 9, 12, so on and so forth. Take a moment, do it, and then come back to the answer. So this one is obviously extremely simple. It's an arithmetic sequence, and un equals, because we're adding 3 each time, and we start at 3, this is simply 3 times n. and you can try it. For example, if we want to confirm it, a u to the fifth would be 3 times 5, which would be equal to 15, which is simply 3 more than 12 itself. So we know we've done a good job of solving this question. Now let's get into some more challenging ones. Let's do this one. 3, negative 12, 48, and let's say negative 192, I believe it is. Yes. So in this case, well, this case, clearly it's not arithmetic because we're not adding the same value each time. That is evidently true. So it must be geometric. So how would we go about solving this question? Well, if it was me up to this, I would break this down into a multiplication, into a set of multiplication. For example, let's just leave this blank. So let's just say 3 times what gives us 3. Well, let's just leave that. Let's move on to the second term because we don't really know what the common multiple or factor is that we have to consider when constructing our general term formula. Let's take this one. 3 times what gives us negative 12? Well, it's 3 times negative 4. What about this one? 3 times 16. Okay, that's starting to establish some sort of trend. And then this one is 3 times negative 64. Now, clearly there's a trend between this multiple, negative 4, 16, and 64. It's simply 4 to the power of something. And in this case, it would actually be 3 times 1, which would be a 4 or negative 4 to the power of 0. So this establishes some sort of trend. So let's break it down. Un would be equal to 3, which is our first term, as we said in the previous example, or our basic example, and our multiple in this case would be negative 4 because we obviously have a negative. So let's plug in this negative 4. And then our power is going to be n minus 1. Why? Because not only for the reason that we need a 3 at the beginning, but also for the reason that we have a negative number and our even terms have to assume a negative count. Why? Because when we substitute in our term number, which is 2 in this case, this will yield us a value of 1. And 1 times negative 4 to the power of 1 gives us negative 4 times 3 gives us negative 12, and so on and so forth for every even term. Turns out to be negative. That's why we have the n minus 1. I will explain more into detail because there's cases where we have n plus 1, and that will come up shortly. Moving on to the next example. Let's take a look at this one. 2, 10, 50, 250, and etc., etc., etc. Now, clearly, obviously, it's not arithmetic because we're multiplying each time by 5. Exactly. So we're multiplying by 5 each time. And essentially what you need to keep in mind here is we follow the same exact routine. Usually on tests and on grade 11, grade 12 tests, these sequences, they tend to follow the same exact format. So if you can get the hang of these, then you should be totally fine on your next or upcoming sequences and series tests. And so this is the way that we tackle this problem. Un equals the first term number, which is 2, times 5 to the, well, you guessed it, n minus 1. It always follows the same exact routine. And how can we verify it? Well, let's just test out the fourth term, or u to the fourth. Well, this would be 2 times 5 to the 4 minus 1, which would give us 2 times 5 to the third, which would be 2 times 125, which would give us 250, which corresponds to our sequence, meaning that we did do the sequence correctly. Next question. This question is a bit more challenging and something unique, I feel like. So let's start off here with 1 over 3, negative 1 over 9, 1 over 27, and so on and so forth to negative 1 over 81, and the list goes on and on. So how do we go about doing this? Well, clearly, we see a pattern. We rotate from 1 to negative 1 in the numerator, and in the denominator, we just keep on multiplying by 3. So this is not an arithmetic sequence, nor can it be geometric. We call this neither in mathematics. And usually, when you tend to get fractions, not always, but when you tend to get these tricky type questions, they are not arithmetic, nor are they geometric. So let's try to tackle this question. Well, clearly, we are not changing, like concretely, we're not changing the numerator, but we're changing the sign that's associated with it. So what we have to say in this case is un equals to negative 1, because every time we're rotating differently, to the power of n plus 1. Why? Because our first term, which is odd, tends to be positive. So the only way we can have a positive odd rotation and a negative even rotation is if we put the exponent n plus 1. Because if the term number is 1 here, we have to have an even exponent to neutralize, but to make the negative sign positive. And that's why we need to add this at the beginning always if we have a rotating negative or positive in this type of situation. And then the bottom is extremely practical because all we're doing here is just putting 3 to the power of n, or 3 to the power of the term number. So what we have to do is, all we have to do is say that negative 1 to the n plus 1 multiplied by the 1 over 3 to the nth power. And that is it. If you want to test to see if we got it right, well, let's just take the fourth term. U to the fourth equals negative 1 to the 4 plus 1 multiplied by 1 to the 3 to the fourth. And that should end up giving you negative 1 over 81. And this is a type of kind of a trick problem. Not the most difficult. We will get to a more difficult problem in the near future. Let's try this one. This one is much easier. It's back to a rotation, but it's different to what we've been doing, all these geometric sequences. So let's transition a little bit. So looking at it, pause the video, try it, but looking at it, immediately we can tell there's a difference. This is an arithmetic sequence. Why? Because each time we are subtracting 6. Every time we're subtracting 6. Therefore, we follow the same format that I mentioned at the beginning of the video. We take the difference, negative 6, we multiply it by the term number and add the remaining difference, which in this case would be 47. And that's your general term. Let's try a couple more difficult questions, and we'll do this word problem that I have to the right, and we will call it the end of the video. Let's try this one. 1, 1, 2, 3, 5, 8, etc., etc. Pause the video, try it, but we'll get into this. So clearly, this is nothing like we've seen before. This is not geometric. This is not arithmetic. We cannot multiply, nor can we add consecutive similar terms to get to the next term. But if we look at it, it's pretty easy to understand. This is actually a very specific type of sequence in which we add these terms to get the next term. And we add these terms to get the next term, because 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3, and so on and so forth. So this one is actually a type of recursive sequence, and we'll get into that in the next video. Please tune in where we do recursive and sigma notation if you need to do that. But in terms of the general for this one, it would be u, right? It would be u to the n minus 1, which is, this represents your previous term. Don't worry, we will get into this in the next video, so please stay tuned and watch that one if you're having trouble with recursive sequences. Plus u to the n minus 2. And what this means is that each and every term that we surpass in the sequence, we're applying the same exact formula. The previous term plus the next term gives us the next term. This is what this symbolizes. And let's move on to our last concrete example, and before we move on to the word problem. So let's try this one. 1 over 2, 3 over 4, 5 over 6, and 7 over 8, etc., etc. So what do you guys think about this one? Clearly, it's sort of an arithmetic sequence, but at the same time, we can't call it that because we're doing two different operations because it's a fraction. And here what we see is we have a plus 2 addition each time in the numerator and a plus 2 addition in the denominator itself. So how can we possibly articulate this into a general term? Well, the general term, if you can see here, if always, when you have an arithmetic, I'm always telling you guys, it's a foolproof way of doing these questions. You take the common difference for the numerator, multiplied by the term number, and then add or subtract the difference that's remaining. In this case, it would be negative 1. Let's just take the first term, for example, because 2 times 1 gives us 2 minus 1 gives us the 1 that we have in the numerator. So that's that. Now, all we have to do is just work with the denominator. And all we have to say here is we have 2, 4, 6, 8, which is our basic sequence. And all we have to do is take 2 multiplied by the term number, giving us 2n. Very simple, very easy, and I hope now you guys are getting the hang of it. But for now, let us take this word problem and finish this video. So let's look at this word problem. It says, for each of the following real-life situations, give the general term and state whether the sequence is arithmetic, geometric, or neither? And the first question says, Ahmad deposits $100 in a savings account every month. After the first month, the balance is 100. After the second month, so the first month is 100, and after the second month, the balance is 200, and so on and so forth. This is a pretty basic arithmetic sequence. All it is UN equals 100n. Very simple, very easy. So this is part A. Let's tackle part B. Luciana is trying to lose weight. The first month she loses 6 kilograms and she continues to lose half as much each subsequent month. So this is starting to look like a geometric sequence. Exactly. So what usually these types of questions are going to pop up in our exponential unit, which we will tackle in the near future. Please stay tuned for that. But these questions obviously is geometric. And remember, every time I told you for these questions, every time we have a starting number, use it. Put it at the beginning, and then our common multiplier factor is half, is 1/2. So what you have to do is you have to plug in 1/2 to the power of n minus 1. And this would be your general term for this geometric sequence. And the last question, for those of you that are still here, is the temperature of the water in the swimming pool in your backyard is only 70 degrees Fahrenheit. It is too cold, so you decide to turn up the temperature by 10% every hour until it is cold enough. Again, these are exponential type questions, which we will get into. I believe it's chapter 9 for the IB textbooks, but we'll get into that soon. But these questions, in terms of the sequence, would be UN multiplied by our starting number, which is 70 degrees Fahrenheit, multiplied by the increase or multiplier factor, which in this case would be 1 plus 10% or 1.1, which we plug in here, and then we say n minus 1. And that is it for the video. I hope you guys enjoyed. We will get into the next portion of the videos, which would be recursive sequences, sigma notation, and then moving on forward into the actual arithmetic series and geometric series and all of that. Please stay tuned. Those will be in the playlist for this first chapter that we're working on. But if you like the video, please comment, please like, please subscribe so we can continue providing this content for you and getting better each time. But most importantly, at RSW Tutoring, we believe that we should make content for the viewers. So if you have any questions whatsoever, we will respond to you as soon as possible. And that is it for this one. Thank you for listening, and have a good night or day, depending on where you are. Bye.